All right, so the meeting is being recorded. We're going to record this and post it online later for anyone who isn't able to attend right now. But we're going to go ahead and get started. And if you're not speaking, the unmute is not controlled, so just please keep your mic on mute unless you are speaking or asking a question. All right, so hi everyone, welcome and thanks for joining us today for this media briefing. I'm Sarah Frazier with NASA's Office of Communications. In a few weeks, the LOFTID technology demonstration will launch as a secondary payload with NOAA's JPSS-2 satellite. LOFTID is short for Low Earth Orbit Flight Test of an Inflatable Decelerator, and this tech demo will be the first orbital flight test of the inflatable heat shield technology that's been in development for over a decade. The entire demonstration will take place within about 2 hours after liftoff. This technology could be a major piece enabling us to land crewed missions on Mars and United Launch Alliance. So we're here to talk more about the goals of the technology demonstration and its potential benefits for future missions are Trudy Kortes, Director of Technology Demonstrations in the Space Technology Mission Directorate at NASA headquarters, Joe Del Corso, LOFTID Project Manager at NASA's Langley Research Center, John DiNonno, LOFTID Chief Engineer, also from NASA Langley, and John Reed, ULA's Chief Rocket Scientist. We also have a couple other folks on the line from the LOFTID team to answer questions. They are Tara Tweeton and Greg Swanson. So when we get to the question portion, we'll have them available as well. So before we get started, we're going to show a short video overview of LOFTID, and then we'll have opening comments from our four speakers, and then open it up for questions. When we get to the question portion, you can raise your hand or put your question in the chat box if you prefer. But if you're not asking a question and while the speakers are talking, we ask that you please stay on mute. So again, please note that we are recording this briefing and we'll post it online after the event. So with that, I will let Kristen start the video and then we'll pass it off to our first speaker. All right, so that should give you a basic idea of what we're talking about here. But now we're going to hear from Trudy Kortes. So Trudy, I'll pass it to you.
Okay, thank you. Thanks, Sarah. Good afternoon. Thanks, everyone, for joining us today. Really cool to watch that video again. Gives me goosebumps every time I see graphic representation like that about what we're about to launch and attempt to accomplish here in a few weeks. So I'm really excited to be here today with my colleagues from NASA and industry to talk to you all about the upcoming launch targeted for November 1st of our latest technology demonstration mission, LOFTID. I'll start out just by saying that LOFTID is a project that has been managed and led for the Space Technology Mission Directorate by Langley Research Center in partnership with a really great partnership with United Launch Alliance. LOFTID, so I'll just explain a little bit. LOFTID is part of the Technology Demonstration Missions program. We have a portfolio of technologies. We're working on a broad range of technologies that go from development to demonstration. Our TDMs serve to, we like to say, bridge the gap that exists between development of technologies and use of that technology in emissions. So how do we do that? We test systems. We put systems together first of all. We do as much ground testing as we possibly can, get them to a technology readiness level, we call it, that's ready for system integration. And then we put them into an environment in which they're ultimately expected to operate. And you just saw that represented in the LOFTID video. We learn a lot during these tests. We use that learning for kind of next versions of the technology, or getting it on the path to operational use. It's usually a multi-step process. So ultimately, these demonstrations basically serve to reduce risk, prove out concepts, improve state of the art, and really develop this next generation technologies that we need and our industry partners need for future space exploration missions and other commercial uses. LOFTID is really a great prime example of that for us. It's exactly all of those things. NASA really would not be able to get space technology to operational status without programs such as TDM. And these demos make future missions possible. So we take that calculated risk, and I always like to say we take smart risk to advance a technology. And so again, LOFTID's a great example of that, and it's even better when we find a partner that also needs our technology. It becomes very synergistic. It's really the best case scenario for us. So to talk a little bit about the mission, although we have several experts on the line with us today, I'm not going to go into too much detail. They are, but the upcoming demonstration is the culmination of about a 5-year-long project. Sarah mentioned this technology has been in work for over a decade. This specific project, LOFTID, has been happening for about 5 years to develop the 6-meter hypersonic inflatable decelerator. So what challenge are we trying to address with this? Basically, just in a few words, landing heavier payloads. Landing heavier payloads in atmospheres and where they can really fit this technology, this hardware can fit inside of a launch vehicle fairing when it's deflated, which opens up possibilities for us as well, instead of a rigid structure, which is limited. This technology can ultimately enable new missions for us to Mars, Venus, even the largest moon of Saturn, Titan, becomes a possibility because of the dense atmosphere there. And it can be used for payload returns to Earth as well. So I want to emphasize something. This LOFTID is cutting edge technology. It's a first of its kind, and we like to say that in TDM often. It's the first low Earth orbit flight test of this technology in the largest scale test article to date, and it's the 6-meter size that I mentioned. So really our main objective here is to demonstrate this technology through the hypersonic regime to obtain flight data and really learn how this technology performs in that environment and just use it for future needs. So I'd just like to finish my portion of what I was going to talk about today, just to get back to the partnership aspect I mentioned a couple times before. So first of all, Langley has partnered with other NASA centers. Ames Research Center, Armstrong Flight Research Center, and Marshall Space Flight Center have all had key roles in this. We're flying with NOAA's JPSS-2, the Joint Polar Satellite System program. It's a NOAA-operated national mission, I'll mention too. That deal was kind of brokered for us by our colleagues in the Science Mission Directorate, and we've enjoyed a really great partnership with them as well. So I'm very grateful to my colleagues in SMD. Our main partner with this, as I've mentioned, is ULA. They've provided hardware, the recovery vessel, in fact, for us to obtain the hardware back once it lands off the coast of Hawaii. And speaking of ULA, I'll just say NASA is most honored to dedicate the LOFTID TDM technology demonstration mission in the memory of Mr. Bernard Cutter. Bernard was a colleague and the manager of advanced programs at ULA who passed away unexpectedly in 2020. He was an advocate for utilizing technologies such as LOFTID to lower the cost of access to space, and a true proponent of that. And again, we're honored to name it in his honor and his memory. So again, from me, thanks for joining us today, for your interest in technology demonstration missions, specifically LOFTID. I'm happy to answer questions at the end after my colleagues have spoken, and back to you, Sarah. Thank you.
Thank you, Trudy. All right, next we're going to pass it to Joe Del Corso, the project manager for LOFTID, and I think Kristen is going to pull up some slides.
Thank you. Appreciate it, Sarah. And thank you, Trudy. As Sarah mentioned, I'm Joe Del Corso. I am the LOFTID project manager. I've actually been working this technology since 2005, since the original payday effort. I'm going to be basically just walking you through some of the technology development history, how we got to where we are, why this technology is important, and then and then I'm going to hand it off to my colleague John DiNonno, who is our chief engineer on LOFTID, and he's going to go through some of the details down and in on the hardware. So HIAD is the hypersonic inflatable aerodynamic decelerator technology. That's what we are demonstrating on LOFTID. The original concept actually comes from the 50s and 60s. Unfortunately, during that time, they did not have the materials or structures. They were not sufficiently advanced enough to actually realize the capability. More recently, one of my colleagues, Steve Hughes, a world-class engineer, picked up the technology around 2003, recommended it to NASA, and with the assistance of PI Neil Cheatwood, we were able to start garnering some funding for the technology. So in 2005, we started our first ground development effort called Payday, the project to advance inflatable decelerators for atmospheric entry. It is a mouthful, I admit. During that ground development effort, it was really very rudimentary, testing proof of concept, whether materials can withstand hypersonic flight regimes. From there, we had a flight test in 2007 called IRVI, the Inflatable Reentry Vehicle Experiment. Unfortunately, due to a launch vehicle anomaly, there was no experiment. So we then were able to fly IRVI-2, the Inflatable Reentry Vehicle Experiment number 2 in 2009, which was an IRVI build to print. We launched out of Wallops. That was a 3-meter scale aeroshell. The sounding rocket that we launched on was the smallest in the Wallops arsenal, and basically it went straight up and came straight back down. So it was a good proof of concept and it worked beautifully, but it wasn't sufficiently mature at that point to do an orbital entry. At that point, we were simply looking at whether the concept works. Because of the success of IRVI-2, NASA invested in a ground development effort, which has become the nomenclature for the technology, called the HIAD ground development effort, the Hypersonic Inflatable Aerodynamic Decelerator ground development effort. That was in 2009. During that ground development effort, we essentially matured material systems, manufacturing processes. We matured our entire infrastructure, how we deal with flexible systems as a whole and flexible aeroshell. From the success of HIAD, the first ground development effort, we then went into a flight test called IRVI-3. During that flight test, we launched again out of Wallops on the largest sounding rocket in their arsenal. Again, went straight up, came straight back down, but this time we had much more advanced inflatable structure, more advanced flexible thermal protection system, higher heating, and we were able to show controllability during entry. From there, we went to another ground development effort called HIAD-2, which lasted up until our LOFTID flight test. During the HIAD-2 ground development effort, we focused instead of just concept and demonstration, we focused on increasing scalability of the aeroshell. We went from 3-meter scales to 6 meters to 12 we looked at going up to 18-meter scale and 20-meter scale with these aeroshell. Now, in 2018, STMD, as Trudy mentioned, started off LOFTID, the low Earth orbit flight test of an inflatable decelerator flight project. This is a demonstration of the HIAD technology at a 6-meter scale and at environments that are relevant now to Mars and human missions. Let's go to the next slide, please. So why is HIAD important? What's the purpose of HIAD? HIAD is a deployable aeroshell. It can be packed and stowed into small volumes for launch and for the cruise phase of a mission. We can then deploy it exoatmospherically or in orbit in order to decelerate heavy payloads and put them onto the surface of any destination with an atmosphere. Why does this matter? Currently, using rigid technologies, using rigid aeroshell, we're limiting the size of the aeroshell itself to fit within the fairing of a launch vehicle. That means that we are limited to about 4.5, 5-meter aeroshell sizes. What does that mean? That means that the larger the aeroshell, the more down mass capability you can put to the surface of a planet. So if you're limited to 4.5, 5 meters, that limits you to about 1.5 metric tons of down mass capability. Using the HIAD technology, we are looking to expand that to 20 to 40 metric tons. The equivalent is massive. 1.5 metric tons is about the equivalent of a very well instrumented golf cart. 20 to 40 metric tons is what you need to put humans on Mars. It is the equivalent of a small, fully furnished ranch house with a car in the carport. The other improvements that we've made and the other benefit that HIAD brings to the table is access to planetary locations. Specifically with the large aeroshells, we're able to increase planetary access in order to reach higher elevations. If you see the images on the right-hand side, the top right image shows the rigid aeroshells are currently limited to the areas in or altitudes with blue. Those are considered the northern lowlands of Mars. With the HIAD technology at 18 to 20 meter scale, we're looking to be able to reach 70 to 80% of the Martian surface, not including some of the mountain tops. Let's go to the next slide. So LOFTID objectives. So LOFTID is a demonstration. It's an orbital entry demonstration and test of HIAD reentry vehicle, specifically for NASA's heavy down mass missions, and we'll apply that to commercial applications as well. We will launch out of Vandenberg as a secondary payload on an Atlas V launch vehicle. John DiNonno is going to go through some of the details of that shortly. And we will demonstrate the HIAD technology at a scale, 6-meter scale, and entry conditions that are relevant for Earth and Mars mission and fusion opportunities. Next slide, please. Finally, I want to thank ULA. Frankly, the NASA and ULA partnership has been outstanding. What ULA is bringing to the table are launch integration services. They brought to the table some adapter hardware for us, as well as our inflation system hardware. In addition, they're also contributing the parachute and mortar systems and the hardware recovery ship so that we can recover the LOFTID reentry vehicle and the ejectable data module that will have the LOFTID reentry data on it. In addition, NASA is contributing project management, safety and mission assurance, technical excellence, as well as the LOFTID reentry vehicle and ground systems. At this point, I'm going to hand it over to John DiNonno, who's going to walk through some of the more technical details of the LOFTID mission.
Thanks, Joe. So yep, as mentioned, we have John DiNonno up next, LOFTID's chief engineer. Go ahead, John.
Hello, thank you, Sarah. So I'd like to get you familiar with the LOFTID reentry vehicle itself. What you see before you is the stowed configuration, as it would be nose up for launch. And the light colored area in the background shows the deployed aeroshell superimposed in the configuration it would be in reentry. So you can see the RV is 89 inches tall and 52 inches in diameter. And the entire aeroshell packs within the 1.5 feet at the forward edge of the nose. And when it's deployed, it unfurls so that the entire RV for reentry is about 6 feet, 71 inches tall. The internals include the inflation system, and I'm pointing to the inflation system tanks in this slide. We have 2 tanks. Those were supplied, thankfully, from ULA, from their flight hardware. We have an ejectable data recorder on the lower left. That system allows us to capture all of the data and eject it from the vehicle as a backup in case we cannot recover the vehicle itself. So it gives us extra assurance that we will retrieve the fully recorded data. We also have a data recorder that stays on board to be recovered with the vehicle. And we also, to aid in recovery, and this was supplied by ULA as well, is the parachute system, which includes a pilot chute mortar that deploys and it extracts the main parachute, which is the large area that's packed in that section. So we divide the RV into segments, and the forward segment includes the inflation system and the structural interface for the aeroshell and the aeroshell itself. The mid segment houses the avionics, which includes the system battery and the control features of the vehicle. And the aft segment is basically recovery hardware, and it includes 6 camera pods that give us both video data and infrared imaging of the aft side of the aeroshell as it re-enters. Next slide. And now I'll go through the timeline and the ConOps for the mission, the concept of operations for the mission. As you can see, climbing from the left, where we launched from Vandenberg, the primary mission, which is carrying JPSS-2 to orbit, it is basically completed in the first 30 minutes of the mission. The JPSS-2 satellite is put into its polar orbit, and the Centaur, the second stage or the upper stage of the launch vehicle, performs a contamination and collision avoidance maneuver. Then it does a transfer orbit to a lower orbit that's not in the same orbit as JPSS-2, and then it deorbits from that lower orbit to ensure that LOFTID is on a trajectory for entry. This entire time, LOFTID is powered off. This is part of our assurance to do no harm to the primary mission. We are grateful as a secondary payload to get this ride share with JPSS-2, and we want to ensure that LOFTID does not do anything to harm that primary mission. So LOFTID is very passive and stowed in an enclosed payload adapter underneath JPSS-2, and is completely powered off until after the deorbit burn is complete. Once the deorbit burn is complete, then the Centaur sends a command that powers on the LOFTID reentry vehicle. And at that point, the Centaur will jettison the portion of the payload adapter that is covering the vehicle. This exposes our stowed aeroshell so that it can be deployed. The LOFTID reentry vehicle sends the start inflation command to the aeroshell, and slowly it inflates until it's at its full pressure for reentry. After the aeroshell is inflated, the Centaur spins up the vehicle, and by spin up, it's actually a fairly slow rotational speed. It's 3 RPM, but it's enough to provide spin stabilization for reentry. And once it's pointed on its exact path for reentry that we've targeted for the environments that we want to see on the aeroshell, the Centaur then releases the spinning RV, and it goes through a ballistic reentry. The Centaur diverts to make sure it's off the path of the RV, and the reentry vehicle goes through hypersonic, supersonic, transonic, and down to subsonic speeds. After it reaches Mach 0.7, we consider that the end of the experiment. After that, the data recorder is ejected. And after the data recorder is ejected, then the chutes are deployed. That gives it a gentle splashdown in the ocean, where we hope to recover the vehicle and the data recorder. So for recovery, this occurs off the east coast of Hawaii, and this graphic gives you an illustration of where relative to Hawaii we'll be recovering, and an example of the vessel that we will be using from the University of Hawaii. This recovery effort is part of the Space Act agreement that ULA is providing, and will help get both the reentry vehicle, which we cannot guarantee will float indefinitely, but we expect it to be floating shortly after the mission, and it will retrieve the reentry vehicle and then retrieve the data recorder. The data recorder we do guarantee will be floating. Okay, next slide. This actually might be the last slide. One thing I did not mention during the ConOps was that we will also be transmitting data in real time from the vehicle. It is a limited data package that we get sent through the Iridium satellite system, and we receive it as an email, and this provides us minimum data. So even if we do not recover any of the assets that re-entered, we should be able to reconstruct the trajectory from the data we receive. And with this, I'll hand it off to our colleague at ULA, John Reed.
Thank you, John. I guess first off, I just wanted to say thank you for the opportunity to join the team here, and especially for the gift of naming LOFTID after Bernard. He and I have worked with the team for years, and I greatly appreciate that, as I know the family does. Obvious to point out that we, ULA, are a space access company. And so you may wonder about this partnership and why we have it, but really it stems from our vision, which is to harness the potential of space for humanity. And that really guides us to having collaboration and collaborative relationships. While this is especially true in advanced programs, it really does reach across the entire ULA team, where our mission success focus really promotes collaboration and ensuring that we're giving the best services that we can to the vehicles and systems that we carry to orbit. I bring that up because really getting to today has been a team effort. Way back when, we were looking for pairing opportunities and trying to evaluate the possibility of secondaries and doing lots of rapids analysis for couple loads and running the wickets on contamination, all the way through once we had the pairing and developing the unique adapter to be able to carry JPSS and encapsulate the LOFTID payload. I think the biggest feature of all of this in our relationship has been listening to each other and resolving the concerns to make sure that we kept everything moving forward. And I would also reiterate that the team that we've had here between the different government agencies across NASA, as well as the collaboration between our team and the NASA Langley team, has just been outstanding. Obviously, we're interested in HIAD for reuse. We've spoken many times about it in lots of different public forums, but really we want the technologies and the solutions that we kind of collaborate in developing to have broad application. And so the whole focus in this effort has been to develop a path that can support not just us, but LEO commercial applications, returning products from cislunar and that marketplace, as well as getting on to Mars and having the downmass to really enable humanity's expansion. So to that end, and with that in mind, we kind of left NASA's focus to be on the HIAD and that technology maturation for the flexible thermal protection system. And we kind of focused on those core things that we would do, both from a normal launch integration, as you saw in that earlier chart, but also those things that have application for our recovery and recovery of our engines. And so we were going after the parachutes and the barge, as well as the flight environments. We did some unique things to have the precision nav to be able to land where we need to for this mission to have the ship be able to recover. And so we kind of brought the best of both organizations together through the collaboration to deliver this technology demonstration mission. And with that, I will pass it back to Sarah, and I assume we'll open it up for questions.
Yep. All right, thanks, John, and all of our speakers. So it is time for questions. Just a reminder that in addition to the speakers you just heard from, we also have Tara Tweeton and Greg Swanson from the LOFTID team on the line. And to ask questions, you can either raise your hand, which I know a couple people have already done, or put your question in the chat if you prefer. And when you're called on, please just state your name and affiliation and to whom you're directing the question, if you have a specific person. All right, so I will start with Irene.
Thanks, Sarah. Irene Klotz with Aviation Week in Space Technology. A couple questions. For Trudy, what is the total program cost for the LOFTID effort? And has the contract given to ULA in 2017 for JPSS-2 launch services of 170 million, has that figure changed at all? And then also just wanted to know when ULA joined the project.
Okay, hi, Irene, thank you for the question. So I'll start out, answer the first part of your question. So LOFTID was funded at just under $93 million. That's total life cycle cost of the project over about 5 years' time, from 2017, October 2017 to now, so just about 5 years later. And I will ask probably John Reed or someone else to speak to the ULA contract portion of your question, Irene.
Yeah, so I guess I'd first clarify that this was an unfunded Space Act agreement, so there were no funds exchanged. NASA's budget was spent by NASA, and we came to the table with the solutions that enabled us to have this pairing. I would say we've been involved before the decision to go with JPSS. Part of the TDM that we signed was to help look for opportunities to make this tech demonstration a real mission. And so we've been engaged in those conversations from the early days back in 2015, 2016. Does that answer the question sufficiently?
Thanks, John. Just to clarify, I know that this is an unfunded Space Act agreement. My question referring to the $170 million contract that was for the NASA launch services for JPSS-2, of which, of course, LOFTID is the companion payload. And my question was whether that launch service contract had changed at all, or if that 170 million is still a good price. So that is probably more of a NASA question.
Yeah,
I'm not the right person to answer that, but I will say there was delineation of effort. So we funded the integration of LOFTID on our own internal IRAD.
Thanks.
And for the launch question, I'll have someone from the launch services program follow up with you, Irene.
Okay, thank you.
All right, thanks. I'm going to go to Jeff Faust next.
Hey, good afternoon. A couple questions about the actual reentry and deceleration. How much deceleration does this provide? How much do you slow down from what speed down to, I think, Mach 0.7? And then what sort of heat loads do you see on the reentry on the decelerator itself, and how are you protecting that from the heat of reentry? Thanks.
John, do you want to take this one? John DiNonno.
Thank you. That's a good question. Yeah, this is John. I can take that one.
Are you there, John?
We may have lost John.
Can someone else speak to that, or should we come back to that when we have John?
Yeah, okay, so basically, sorry, John, I'll jump in real quick. Basically, as far as heat flux, we're looking at about 40 watts per centimeter squared. And I have to admit, I don't remember what the heat load is off the top of my head, but we are looking to decelerate from 8 kilometers per second, or about Mach, I think it's Mach 25 times the speed of sound, down to subsonic. So Mach 0.7 is about where we say that the mission profile has ended, and that's when we're popping parachutes, the parachute system.
And then how are you protecting the decelerator from that heat of reentry?
So, all right, so the HIAD technology is basically a set of inflatable torus in a stacked configuration. And then over the front of that, we have a flexible thermal protection system. It's two key parts. The inflatable torus structure, the inflatable torus provides the structure for the aeroshell. When people think of those torus, they tend to think of those inner tubes you float around on a lazy river with. That's not what these are. These are closer and likely and they're closer in kind to the wheels on your car. They're very, very rigid. And then the flexible thermal protection system is a series of material layups specifically designed to withstand the aero heating and loads for this particular reentry. And we can tailor that to different atmospheres, different environments, different thicknesses. So for this particular mission, we understood what the entry was going to look like. So we've tailored it specifically for this entry. Think of it like a firefighter with a fire jacket going into a fire.
All right, thanks. I think we did get John reconnected, so we should have him for future questions. All right, next I'm going to go to David Curley.
Thank you very much. A couple of questions, bigger picture. John Reed, ULA came in because you want this technology to help you recover your engines. Is this another example of the private-public cooperation and through the research phase to make something work? And then a more general question for the engineers, does this end up, if it all works and what you think is going to happen happens, does this end up becoming the UPS, the Amazon, whatever, just dropping cargo on planets and places that you need it and you just go pick it up?
So I will say, yes, I think this is an outstanding example of public-private partnership where we bring our expertise and NASA brings their technology understanding together to help another supply base emerge to support the broader community. I would caution against having too many visions of HIADs falling out of the sky to everybody's home. That'll create issues that probably are best addressed by the FAA.
Yeah, so I'll I'll say that there is application. There are specific applications that we have looked at for this technology, namely smart reuse being one of them for lower cost access to space. The other one is being able to put large payloads onto the surface of Mars. We've done a number of trade studies, almost a dozen at this point, over the last 10 to 12 years, looking at various technologies, down mass capabilities, and technologies. And what has come through is that LOFTID provides the largest mass, the largest opportunity for higher elevations. And given if you had to choose between a HIAD or say retro propulsion or rocket-based systems, you get a savings of somewhere on the order of $1.8 to $2 billion using a HIAD over retro propulsion, just in mass savings, what you have to send to a planet. No, I don't see this being used to drop Amazon packages into your backyard, but we have had some interest in space tourism, being able to utilize these the HIAD technology for escape capsules, as well as for retiring ISS key components that are too large to bring down currently with our current technology. Given that shuttle has been retired, we don't have a heavy down mass capability at this time. So HIAD is one of the key options for helping to bring back some of those really large payloads from ISS.
No, I was suggesting that it might be the Amazon to Mars or the moon, not to my backyard. When you mentioned escape, is that kind of how the technology started in the 50s and 60s? Was escape from orbit?
So the technology in the 50s and 60s was very much in line with what we're currently doing. I don't believe it was an escape capability. That's just something more recent that's come up. National Geographic was looking to to do an actual jump from space, and they approached HIAD about 5 years ago looking to do that. And at that time, technology was not at a point where I'd be willing to put somebody's life on it yet, but it will be soon.
Joe, I think one other thing worth pointing out, when we were in the early days of formulating the LOFTID mission, we did have conversations with people that were interested in producing things in low Earth orbit. And so I do see there being a downmass market for using this technology to bring goods back to the surface of the Earth from the commercial LEO infrastructure.
All right, thanks everyone. Before we move on to the next question, now that we have John DiNonno back, I think Jeff, part of your question was about the max heat load on the aeroshell, is that right? And John, I don't know if you have that figure.
Yes, I'm sorry. I'm having some connection issues here. So the max heat load is about 18 times more than we were able to accomplish on the ERV-3 mission. And it's on the order of 3.5 kilojoules per centimeter squared.
Great. All right, for the next question, this is from Yukuro Inokuchi of Kyoto News, and they ask, how do you judge if the experiment is successful? What will we know on the day of the experiment? And will you judge if it's successful or not? So I'll let whoever is appropriate answer that.
Right. So I think I'll take this one if that's all right. So we have very specific level 1 requirements that we're trying to meet. Number one, we want to know that the vehicle has been set up properly for entry. It's on the correct flight path angle. And as John mentioned, we do have a little bit of data coming in real time, as well as being a full data set being recorded on board and on our ejectable data recorder. What we're going to be looking for is that the vehicle was set up properly, that the data shows that it's oriented properly, and then in the initial data bursts that come back through our satellite system, we're going to want to show post-entry that it is still oriented properly, and that we have we've slowed down, that our position, velocity, and orientation are correct and within the bounds of what we expect to see for this demonstration. We plan to have real-time data coming in, but it'll be data bursts. On the ship, we've got a TRAT system. It's an IR-based system that will be looking up. We will have real-time communication with our ship, who will be doing the active recovery, and the hope is that we should be able to give some preliminary feedback on the day, within at least a couple of hours of re-entry, saying that yes, we believe, based on the data we have, that it was successful or not. Anything more than that would be speculation at this time.
Thank you. All right, next up, I'm going to pass it to Aiden, who had a question.
Hello, my name is Aiden Deleyenfeld from the Asahi Shimbun. My question is, this might be a silly question, but I'm wondering if the deployment of the aeroshell or the heat shield will be visible at all from Earth by any mechanism, or if there'll be any kind of live stream of that or anything.
This is John. I can attempt to take this question. We do have a camera that the Centaur uses, looking forward to release payloads. It will be up looking at the aeroshell when it's inflated. It'll only be a small pie wedge of it because of the field of view. And then we also have cameras on board the vehicle. It won't be a live feed. The data is too heavy to transmit in real time on this mission, so it will be something that they provide to us after it's been downloaded to a ground station before the Centaur re-enters.
Thank you.
Mm-hmm.
Great. Next, we'll go to Jackie Waddles.
Hey everyone, thanks for doing this. Jackie Waddles at CNN. So I was just curious if all of this goes well, what's kind of a reasonable timeline to think about for when we could see this on an actual mission? And is there a specific spacecraft or mission in mind to use this on for the first time? Thanks.
I think I can start. I think it's very preliminary to name a mission that we have for this. I think some of those haven't, even been planned yet. And I'll just emphasize that, this is risk reduction. We're learning. This is the first time we're doing this. Certainly, we have talked about next steps in this suite of technologies, which we call entry, descent, and landing. And there's a scale up that we would begin to talk about and begin to work on. And I would say that both our industry partners and NASA need that scale up to happen to larger sizes, and that comes with its own challenges. But that would be a next step. And then we'll start to talk internally at NASA to our mission directorate partners about those future missions that we could plan using this technology. So great question. Probably a little bit preliminary to cite some there.
Thanks. All right, next let's go to Mike Wall.
Thank you. Mike Wall from space.com. Just a question, how much of this is an extension of the SIAD program? Are these technologies, does this build off of SIAD? Is there a lot of overlap, or is this kind of starting over because SIAD wasn't quite as ambitious? Could you just talk a little bit about that? Like maybe the LDSD test, did they kind of pave the way for what we're about to see too?
So if you don't mind, I'll take this one. Basically, HIAD is actually the precursor to SIAD. We developed the SIAD program at Langley and then gave it to JPL to utilize as part of LDSD. And they did a great job, but that is the supersonic version of this, and it was much lower environment. So no, this isn't really a spin-off or the next generation of SIAD. What this is SIAD was a good benchmark and helped kind of show that the technology can work not just in hypersonic regime, but also in supersonic for a different application. But no, in this particular case, the HIAD technology, this is definitely the parent for SIAD.
Well, thank you.
All right, we have about 10 minutes left in our scheduled time, and I know there's another briefing right after this, so I'm going to go ahead and give some closing details, but then we can keep going as long as y'all have questions. And I mean, they might have other meetings at some point, but for now. So we have been recording this, and we'll post a recording after the fact. So I'll share that link with everyone who was on this call. And then if you do have any follow-up questions or want to request individual interviews, you can email me or my colleague, Kristen Domadeo. We'll put our email addresses in the chat, or Jarell Dodson, who you RSVP to, can also connect you with us. And then after we wrap this up, we hope that you'll stay tuned to LOFTID and particularly watch the launch and coverage of the demonstration on November 1st. So the launch will be covered live on NASA TV. That launch window opens at a nice early 2:25 a.m. Pacific with a 36-minute launch window. And the NASA TV coverage will run through both the launch, the deployment, as well as the full LOFTID technology demonstration. So we'll share the data and reactions in real time as the demo unfolds. So keep an eye on nasa.gov/live for details of exactly when that coverage will start as we get closer to the launch and demo on November 1st. All right, so we're going to continue through questions right now. So just a reminder, you can raise your hand. I do see a few hands still up from people who we've called on. So if you have another question, leave it up. But if you're done, you can take it down. And reminder that in addition to our speakers, we also have Sarah Tweeton and Greg Swanson from the team here to answer questions. And I should have mentioned earlier that Greg will actually be on the boat that's going out to recover the aeroshell. So just a heads up on that. All right, I know at least one other person had a follow-up question, and I see a few hands are still up. So we're going to continue with questions now, and I know that people may have to drop off as we approach 2 o'clock Eastern, but we will keep going as long as we can. So I'm going to call on Irene, who I know had another question.
Thanks, Sarah. John, could you put that 3.5 kilojoules per kilometer second square into Fahrenheit or Kelvin temperatures? And I had a couple of other technological questions, which is what gas is used to inflate the HIAD, and what will be the inflation pressure?
Okay, good questions. In terms of the heat load, that's a energy per unit area. So we use, in this case, kilojoules per centimeter squared. The max temperature we're going to see is somewhere on the order of 2,600 degrees Fahrenheit. But it's the aeroshell is going through multiple environments at once. It's not just heating, it's the loading. So we expect to see over 9 Gs in deceleration, and that inflatable structure is inflated strong enough to be very stiff against that load. We use nitrogen to inflate the structure. And I think I do have one go back. I think I misspoke when I said 18 times. It's actually 180 times the heat load that we saw on RV3. I was only off by a factor of 10. Did I answer your questions?
And the inflation pressure, the pressure once the HIAD's fully inflated?
We're taking it to 19 psi.
Thanks. And one quick one for John Reed. Is this, or will additional tests be needed before a HIAD would be used for the BE4 recoveries, or is this as large as you need to go to demo what you'd need for that?
No, we've talked publicly before about 12-meter-ish size would be required for Vulcan reuse. And I think we'd have additional tech demonstrations and development testing that would have to go on before we'd get there as well.
Thanks very much.
Thank you. All right, Aiden?
Sorry, I just realized I forgot to lower my hand. Go
Okay.
ahead.
All right, I don't think I've seen any other questions in chat messages. If you do have a question, please raise your hand or pop it in the chat. All right. Okay. Well, if no one else has any questions, we can let folks start to hang up. I put my email address and Kristen put hers in the chat box. So again, please follow up with us if you have any follow-up questions or want to arrange one-on-one interviews. And we hope you'll tune in for the JPSS-2 and LOFTID launch on November 1st. And other than that, thanks for joining us. And we'll end it here. Thank you.
Thank you.